Our next common set of polar curves are called petal curves. They're called petal curves because they kind of look like a flower sometimes. These are the form r is equal to a, some constant, times sine of n theta or cosine of n theta. And traditionally, n takes on the form of natural numbers. 1, 2, 3, etc., right? All right, they fall into two categories. One is when n is even, as it turns out. When n is even, we end up with 2n petals in our picture. And when n is odd, we end up with just n petals. All right, but let's look at a particular example of this case where n is even. So r is 2 sine 2 theta, so n has a value of 2. What do we expect? 2n petals, 4 petals. All right, now the key is here to find the angles easiest to graph. What I'm interested in, again, like I was before, is where does the sine function hit its highest, lowest, and is 0. And just like above, those values were what? 0, pi over 2, pi, 3 pi over 2, and 2 pi. But now my angle is not theta. What is it? 2 theta. So I set 2 theta equal to those angles where the sine is highest, lowest, or 0. And then I might have to keep going to be able to trace out the whole curve. But when I set 2 theta equal to this, then what's theta? Well, I have to take each of these values and divide by 2. So the angles I want to look at are 0, pi over 4, pi over 2, right, which is pi divided by 2. 3 pi over 4, which is 3 pi over 2 divided by 2. Get it? And I keep going. And I keep going until I trace back to where I started. Okay, so that's how I get these angles right here, if you're curious. I set 2 theta equal to where the sine is highest, lowest, or 0. Now, once I get those angles, I can plug them into this equation right here, and I get those following points. Okay, 0, 0, because sine of 0 is 0. That means I'm at the origin. When theta is pi over 4, 2 times pi over 4 is pi over 2. And the sine of pi over 2, that's the largest place where sine is. It's got a value of 1, right? So pi over 4, 2. Pi over 2, I'm back to 0. 3 pi over 4, I'm at minus 2 because twice 3 pi over 4 is 3 pi over 2, and the sine of 3 pi over 2 is minus 1. Get it? All right, so you should be able to go through and each one of these values figure out what the value of r is, and that tells me where I am on the graph. Okay, so let's trace this graph through. I start at 0, 0, I'm here. Then I'm at 2 pi over 4, that puts me up here. That's the tip of one of those petals. And then at pi halves, I'm back at 0 again. At 3 pi over 4, I have a value of minus 2. Now here is 3 pi over 4, it's over here, but since the radius is negative, it gets reflected. That's minus 2, 3 pi over 4, right? So I go there, 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 and then down here. And then I'm back at the pole again at what? 0 pi. And then at 5 pi over 4, I have a value of 2. That's this point right there. And then at 3 pi over 2, I'm back to 0. Get it? And at 7 pi over 4, I'm at minus 2. Well, here is 7 pi over 4 all the way down here, but if I'm at minus 2, it gets reflected. And so I trace this curve out like this. And at 2 pi, I'm back to the origin again. Okay, so how do I get these angles? Where the sine, that's this function, is highest, lowest, are 0, right? Plus 1, minus 1, or 0. That's how I pick those. That's how I draw this. And then I get a feel for what the curve looks like. Hey, 4 petals. Notice I will have traced the entire curve as theta runs from 0 to 2 pi. That's not always the case. Let's look at another example of a petal curve. R equals cosine theta. Now n has a value of 1, which means n is odd. And if n is odd, remember, I just get n petals. So I expect n petals. So what does a curve look like with just 1 petal? The answer is it's a circle. Again, I ask myself, where is cosine largest, smallest, or 0? And when the angle is 0, cosine is largest. When the angle is pi halves, cosine is 0. And when the angle is pi, cosine is minus 1 smallest. And if I plot those points, I go from 1, 0 to 0 pi halves. Now, minus 1 pi, well, pi puts it over here. But if it's minus 1, it's a reflection. That's how I end up back here. So that's the piece I trace out. Close enough for government work, I claim it's a circle. By the way, notice that when it's odd, I trace out the whole curve as 0 as theta runs just from 0 to pi. Back here when n was even, I had to go from 0 to 2 pi to get the whole curve. All right, now how can I just look at that? Here's a little review, if you will, and tell that's a circle. Well, I could convert it to Cartesian. How would that go? R is cosine theta. The trick is multiply both sides by r. Why? Because then you get r squared is r cosine theta, but r squared is x squared plus y squared. See, I like r squared if I want to convert to Cartesian, because I know r squared is just x squared plus y squared. R cosine theta is just x. And there's my curve. Just for fun, I'm take that curve, put it in standard form for a circle by completing the square. I pull the x over the other side. I group my x's together, my y's together. Completing the square, I have to ask, what do I want to add here to make it a perfect square? The answer is half of minus 1 squared. That's where I get a quarter. There is its perfect square. Y minus 0 squared, and if I added a quarter to this side, I had to add it to this side. That's how I get that. I'd like to remind you that the general equation for a circle with center HK and radius 1/2, we've seen that before, is this. So what is this? It's a circle with center at 1/2, 0, and radius 1. Makes sense? Now, I'm going to look at another petal curve. R is equal to the sine of 3 theta. Now, n is 3, which means n is odd, which means I expect n petals or 3 petals. All right, which points do I pick out? I pick out the points, again, where this function sine is biggest, smallest, and 0. And those happen at 0, pi halves, pi, 3 pi over 2. Same angles we started with at the very beginning up there. But they're no longer equal to theta because my angle now is 3 theta. So I set 3 theta equal to those. which means to solve for theta, I divide everything by 3, and that's how I get these points, these values of theta: 0, pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and pi. Now I go through and evaluate each of these points. I'm really kind of laboring the fact to review plotting polar points again. First point, 0, 0, so here I am. Second point, 1 pi over 6. Well, there's my angle pi over 6, radius is 1. Third point, 0 pi over 3. Remember, anytime r is 0, I'm at the origin again. The next point is pi halves. Well, pi halves would be up here, but r is minus 1. That's how I get down there. So there's minus 1 pi halves. So I go there, there, there. And then after pi halves, at 2 pi over 3, I'm back at 0 again. At 5 pi over 6, 5 pi over 6 is just pi over 6 short of pi. So that corresponds to this angle right there. I have an r of 1. It's positive, so I'm just there. And then at 0 pi, I'm back to 0 again, right? And I've expected 3 petals. I've gotten all 3, so I know that I have traced my curve out. All right, I think I'm going to stop there. And that is the bottom line on petal curves.